Hello everyone and welcome on today's video. My name is Wouter Peer and I'm the founder and main developer of GG2 Cloud. And today we will be going over another exercise together. And this time we will be talking about irregular configurations. So the example case of today is again a real life case. It's a multi-utility building which for privacy reasons is again replaced by an AI generated image. But it's a building with some stores, with some residential, with some commercial and offices. And the goal of this video is to show you the difference between the borehole length and the borehole depth. Now, we already talked about this when we were discussing tilted boreholes some months ago, but it seems like there is still some confusion related to this concept. And in today's video, we will be looking at a more complicated case of this difference, and I hope it will be clear after this. We will be also looking at the importance of the bury depth. Now, in not all software tools related to borefield design, this is an important or required parameter, but in GG2 it is. And we will discuss how it influences your final design. And then, last but not least, we will be also talking about the irregular configuration itself and why it can be important to use the real coordinates of your boreholes instead of just using standard configurations and how this impacts your results. But first, before we get started, let's go over some of the input parameters so we know what we're talking about. So we will be working with temperature limits between -2 and 25 degrees Celsius. We have active cooling in this case. Simulation period rather long, 50 years, and the first month of the simulation is January. We have some general ground properties, 1.6 watt per meter Kelvin as a conductivity and a volumetric heat capacity of 2.4 megajoules per cubic meter Kelvin, surface temperature of 10 degrees Celsius and a certain geothermal flux of 0.08 watts per square meter. For the borehole resistance, we will be using a single DN32 with a slightly better grout of 1.8 watts per meter Kelvin and 25 volume percent of monopropylene glycol and 40 liters per second for the entire borefield as a flow rate. Now for the load, instead of, when compared to our other videos, we will be now working with an injection and an extraction load. So instead of having the building load, we have the ground loads. And because this is a multi-utility building, there were quite a lot of different demand profiles, etc. So in pre-processing, we determined manually what the ground load will be in this case, so it's easier to simulate that way. And we have 475 kilowatts that directly comes out of the ground, with 477 megawatt hours per year of energy that is being extracted. And for injection, it's 400 kilowatts with 380 megawatt hours per year. Then onto the star of today's video, it's the borefield. So it's 90 boreholes in an irregular configuration, which looks like this. So as you can see, it has something of a rectangle here or an L shape if you're very creative. But this is very difficult, as you can see, to make a simulation as a first estimate. So in this project, the first estimate was a rectangle of 5 by 18 boreholes. And the borehole to borehole spacing was set to 5.5 meters. So this is the first estimate we will be looking at, we will be simulating, and then we will compare it to the actual strange amorphous design like the one below. Now, this was it for the configuration. When it comes down to the borehole depth, we have this cross section of the project, basically. So we have our ground floor, the first level of our building, being at 5 meters above sea level. So that's really our surface level. Then there was an excavation pit created for the cellar of this building. And during construction, they dug it until the level of 0 meters above sea level. And then they started drilling. And after the drilling was completed, the excavation pit was again lowered with 3 meters above sea level, minus 3 meters above sea level, so 3 meters below the sea level. And this is basically the floor of the cellar. So it's the lowest level of our construction. And below this, half meter below this, our horizontal connections were created. But basically we're drilling at 0 meters above sea level. And our drilling depth was 140 meters. We install our single DN32 probe in it with a weight that has a length on its own of 1.5 meters. So this is the situation we have. Now I want to recap some of the terminology before we jump into GHG2 so we know how we can convert this situation to a simulation in GHG2. So in GHG2 you have 4 different concepts and you can use both interchangeably to enter your project into the software. We again have our ground surface at which your ground level of your building is. It's the first level of the building. And then we have something which is called the buried depth, and that's the difference between the ground surface and the level at which your horizontal connections are installed. Then we have something which is called the borehole length, which is the active length of your vertical heat exchanger. So starting at your buried depth, going all the way down to your borehole, this is the length of your pipe itself where it can exchange heat. It's the borehole length. The borehole depth, in contrast, is defined as the difference between the lowest point of your borehole to the ground surface. So either you enter your borehole using the ground surface and the borehole depth, or using the buried depth and the borehole length. Now, given this, we will jump into GHG2 and we will work out how you can enter this project into our software and how it makes an impact or a difference in the results. I see you in a second. So here we are in GHG2 Cloud. I created a new project and I already filled in some of the parameters we discussed, like a minimum maximum limits. We have our ground properties. We have our single DN32 probe with 25% of monopropylene glycol and a flow rate of 40 liters per second for the entire borefield. And for our thermal demand, we used a geothermal load with a certain extraction and injection power and a profile for the base load extraction and injection. But what we did not yet fill in was exactly the start of this video, which is the borefield. So as we discussed, we will start with 5 by 18 boreholes with 5.5 and 5.5 spacing. So far so good. Now the problem is, how will we enter this borefield? Will we use borehole depth or the borehole length? Now, and the example will pop up on the screen. If we use the ground surface, we know the ground surface is at 5 meters above the sea level. And we know that our borehole starts actually at, or is being drilled at 0 meters above sea level. So we know that if we drill at 0 meters above sea level and we drill 140 meters deep, that when we compare it to the ground surface itself, it has a borehole depth of 145 meters. So instead of, we need to change our point of reference not to the level at which the borehole starts, but the level at which the ground is actually at. So that's why it's 145, although only 140 meters is drilled, because we have this extra 5 meters on top. Now, for our buried depth, as you recall, the buried depth was the difference between our ground level, or first level of our building, with respect to the level at which our horizontal connections are installed. Now, our horizontal connections are installed half a meter below the final excavation level, which on its own, it's 8 meters below our initial surface level. It's 8 meters because it was 5 meters above sea level, and we excavated to -3 meters above sea level. So our buried depth in this case is 8.5 meters. Now, if you want to be very strict, and you say, well, okay, we have also a weight that is being installed in this borehole, which has on its own also a length of 1.5 meters. This 145 meters should actually be lowered by 1.5 meters because we have this this metal at the end. But for this case, we will leave it as is. So we have a borehole depth of 145 meters and a depth of 8.5 meters. Let's go ahead and simulate this scenario and see what we get as a result. So we see 90 meters and a minimum average fluid temperature going below our threshold of -2 degrees. So let us now go ahead and duplicate this scenario, and to show you, we will just recreate the scenario, but now using the borehole starting at the buried depth. So what we have now here is that instead of working with the borehole depth, we will be working with the borehole length. So this is the actual length of the horizontal or the vertical heat exchanger, which was our 140 meters, which was being drilled, minus the 3 meters that will be excavated afterwards, minus half a meter for the horizontal connections. So it's basically 140 minus 3.5, which is, if I'm not mistaken, 136.5. Now, our buried depth, that does not change. Whether you're using the ground surface or the buried depth as a reference point, it's still the same 8.5 meters. So if you now simulate this scenario again, you will see that you end up with exactly the same situation as before. So just to show that whether you enter it as the ground surface with 145 meters or the buried depth with 136.5 meters, it's exactly the same. So it does not change your results. So going back to the results, we see that this is indeed not a very good result. It's below the threshold, let's say. Now, I now want to illustrate what the importance of this buried depth is. So if we, for example, say we make a third scenario, we go back to our borefield and we say, well, imagine this borefield does not start 8.5 meters below the surface, but it starts at, let's say, 0.7 meters, which is traditional when you're working with just a plain field under which the boreholes are installed. So we say it's 0.7 meters here. If we now simulate this scenario, what you will see is that it changes the average temperature on the long term quite a lot. So we were at minus 2.7, we are now at minus 2.35. And the reason is that the closer you are to your ground surface, you not only have your regeneration coming from your geothermal flux from below your borefield, but you also have regeneration from the environmental temperature going back into the ground. And of course, if you're under a building 8.5 meters below the ground surface, this is an effect you don't see because there's too much insulation basically. So that's one aspect. The other aspect is that since you're now changing where your active length starts, so we now start at 0.0 meters below the surface, we have a certain average undisturbed ground temperature. But if we say, well, we start deeper under our building with the same borehole length, we have a higher undisturbed average ground temperature. So that's also another effect that we need to take into account. So we have a different undisturbed ground temperature, and due to the fact that we're closer or further away from the ground surface, our long-term behavior changes as well. So now this was a situation for, let's say, our first estimate, our 5x18 borehole. Let us go ahead, duplicate this again, and let's call this scenario 4 irregular configuration. So what you then do is you go to borefield, you'll go to our customize step, and here you can just load the borefield as coordinates. So I've prepared this, I can import the coordinates like this one, my X column and my Y column, and I will overwrite the existing 0, 0 borehole here. And here you can see exactly our configuration. So let's go ahead and calculate with this irregular config. And this is the result. And here you see that all the parameters are the same, borehole length, etc. Our undisturbed ground temperature, of course. But we see that our minimum average fluid temperature is a degree higher than it was in our previous cases. So when we were working with our assumption of a regular configuration, we were far below our allowed threshold of -2 degrees. But when we're working with the real irregular configuration, where the boreholes are all scattered around, it's minus 1.7 degrees. So this stresses the importance of using the real coordinates, the real as built, or the real situation actually. Because, and that's an important difference between GHGTool and other software, we actually calculate with this. So it's not converted to a regular configuration, we really calculate with this specific situation. And as you can see here, it actually makes quite a lot of difference, because with this irregular configuration, your design is actually good. It's above the limits you set. But if you use a regular configuration, yeah, you're not okay in this case. So I hope this video was clear to you, and that when you have a complicated project, that you also try working with our irregular configuration module in GHGTool and upload your own coordinates. You can draw them on an AutoCAD file and you can import it. That's also linked in the description below. If you found this video interesting, consider subscribing, sharing it with your colleagues. Continue learning, continue to design better borefields. And I'm looking forward to seeing you in our next video. Take care. Bye.